I believe so.
Okay,
Yeah.
so what's just figure out what the next number is and go to that slide.
Okay. Give me 1 second. Let's do 29.
Wait, somebody now, wow, I am not 100% sure. Emily asked a question, but that was at 7:08, so that probably was answered somehow. So I'm going to pretend that was answered because I don't know exactly what we were doing at 7:08. Okay, so Linda, show us the slides, please, and we'll look at the problem, and we'll give whatever it is a go.
Okay. 1 second. That's 25. There we go.
Okay. And let's see, I wasn't looking, it looks like there's, I don't know, 19 people are back, or that's counting us, 17 people are back, so that's good. Okay, so now I'm going to read this problem and we'll talk a little bit about it. And I got to tell you that, you know, this is a good problem. It's a probability problem. Okay, so this is called acceptance sampling. And this is really the way things do happen in industry. This is also what you do if you get medical supplies. You don't test every piece of the medical supply, every vial, but you maybe test a couple of them. So that's what happens. So suppose you just received a shipment of 100 televisions. Although you don't know this, 6 are defective. So the problem is telling you that 6 of these TVs aren't working properly. But you don't know that. And by the way, if you had a supplier who's giving you 6% defects, you probably want to switch suppliers, but that's what we have right now. So 6 are defective. But you're trying to determine, do I accept this shipment? So you randomly select 5 televisions and you test to see if they work. So you're picking 5 out of the 100. You're picking to see if they work. Now, if all 5 work, you say, yes, I accept the shipment because that was a sample that you were looking at. Otherwise, if even one of those TVs doesn't work, you reject the shipment. You say, no, it failed the sample test. So what's the probability of accepting the shipment? Now, Linda, I think I can draw on this chart. And so I'm going to be drawing up here with you all. And then Linda is going to go to Excel and actually do this calculation, but we're going to be talking about the theory of it up here. Okay. So what we're going to do is we're going to say that what's the probability you accept the shipment? Okay, well, the probability, how many of the TVs are good? There were 100 televisions and 6 are defective. So there are 94 good TVs. And you're choosing, so this is 94 choose, and you're choosing 5 of them down here. So there's 94, choose 5. And I'm going to do this now. I am going to do this, and this little dot that I'm making here is a multiply thing. But then I'm also going to say that there are 6 defective, and we're choosing 0. Now you might say, well, Jim, you don't even have to do that choosing 0, but what I'm trying to show you is the general form. So you see, you pick the good ones, and then you pick the bad ones, but you see we didn't pick any bad ones because we're saying that we're accepting the shipment, so everything we picked was a good one. Okay, so this is counting how many different ways can I pick 5 good ones. So it's 94, choose 5, divided by, and this I'm picking 0 bad ones. Now the thing I'm telling you is that this number and this number are going to add up to 100, and this number and this number are going to add up to 5. And we will do probably more complicated problems where you have to do that. Now this is the numerator that Linda is going to have, because that is counting how many different ways could you pick 5 good televisions, and that means you're accepting the shipment. Now I have to divide this by, and I think I'm going to ask somebody to volunteer, and if no one volunteers, I'll just answer it myself. In a normal class, I would ask Linda, but I'm trying to save Linda's voice. So I won't ask Linda, but I'm going to ask you, what goes in the denominator here? Okay, so how many different ways can you pick 5 TVs out of 100? And again, I'm not asking you for a number, I'm asking you for the formula. It is anybody volunteering? And again, I don't count it a negative thing if you get, Kathy, go.
Can you repeat the question? Sorry.
Linda's already answering the question.
Oh.
So it's 100 choose, it's 100 choose 5. Okay, so I'm gonna, and Kathy, because of the way you asked that question, I'm gonna, do it again. You see, when you're doing probabilities, you say, what's the probability of something that happening? Well, you say, well, what's in the numerator? How many ways is it true? So I had to count how many different ways can I select 5 good TVs, because I want the probability of accepting them. So there are 94 good TVs, and I'm choosing 5. So this is the formula, 94 choose 5. Okay. But then you're going to divide that by the total number of ways you could have picked those TVs. And you could have picked, there were a total of 100. And if you're picking 5 of them, there's 100, choose 5. So what I was trying to ask you guys was, what is in this denominator? Now, what Linda is going to do is, she's going to go to Excel, because the best way to do a problem like this is with Excel. And she's going to do this 94 choose 5 times 6 choose 0, and then she's going to divide it by 100 choose 5. And I would encourage you guys to follow along, and if you can open another tab where you have Excel, practicing this along with Linda is a good thing to do. Again, that's what Linda and I do when we're in the classroom. I know we're not in the classroom, but we are in the same plane, and we're going to the same destination, and I want you to land successfully. Okay, so Linda, you're going to Excel, and you're just going to pound these things in, I think.
Yep, I already got them.
Okay, so she's changing the channel to Excel then.
Okay.
Okay, and maybe Linda will label that a little bit with just words. So that is going to be, that's the numerator. And you're dividing by the total number of ways. But the formula, and Linda will check on, will click on the formula and show you. And if you look up there at your formula, you see it is 94 choose 5, and she took it times 1, like I was showing her. And when she goes over to this 1, you're going to see that is 6 choose 0. See, if you had 6 things, how many different ways could you choose 0 from it? Well, there's only one way. You didn't pick any of them. And then in the denominator, it's going to be, she'll click there too, and that's going to be 100 choose 5. And you divide those 2, and it's the 54 number divided by the 75, and you get 70. It's almost 73%. So you see there's about a 73% chance that you're going to accept that shipment. Now, Linda, I don't know if you want to put the words on the problem on this Excel spreadsheet, or if you don't want to do any of that, but I'm going to ask the students, do you have questions on this problem? Emily has her hand up. Emily, go ahead. Yeah, Emily, anytime. I'm not sure if Emily had her hand up or not. Yeah, there she is. Yes, Emily.
Okay, can we just get a quick demonstration of how she actually put the formula in?
Okay, sure. Okay, so what Linda's going to do is, first of all, she types an equal sign. And the reason you type an equal sign is that you always type an equal sign when you have an Excel formula. And it will start showing it, but this is the combination formula. And the combination formula then is, and it tells you what to put in. So this is going to be parentheses, and let's just do the numerator. So this is going to be 94, comma, 5. That means 94, choose 5, and then she closes the parentheses, and she hits enter or check mark or something, and she has that number. Emily, did that answer your question?
Yes. So then would we just do 6, choose 0, and then multiply that, and
She's
then
going to, yeah. In fact, she'll show you. She click there. That is combination 6, choose 0. And then she multiplied those. Now, when you multiply by 1, that's just whatever you had before.
right.
So Linda probably didn't actually do that calculation because she's, she does all that in her head.
Mhm.
But you certainly could. And then this next one, show them the 75 thing too, Linda, if you will. So there, now this was the denominator. That's 100, choose 5.
Okay.
And so you should get that. And then this next line is, and you're going to see an equal on this next line because Linda's making a formula. So it's equal, and she clicks on the top one, and then she clicks on the bottom one, and she uses the slash because that's how you do divisions.
Okay.
All right, that's good.
Thank you.
Okay, any other questions before we move on? Okay, Linda, that's good. Let's find the next problem we're going to do then, Linda, please.
Okay. Then let's do 10. That looks like fun.
I have no idea what these are. I mean, I thought it would be more fun jumping around, but maybe not. Oh, wow.
So probably not.
Well, let me tell you what the problem with this. Let's go back and look at it anyway. Okay, let's go back and look at it because I don't want to blow it off. Go back to there. Okay, now I want to talk to the students about this problem even if we don't do it. Okay, but we might do it too. Okay, so this says I think we can do it. But there's what it says. The data set Tornadoes 2017, located at www.pearsonhighered.com/Sullivan Stats, contains a variety of variables that were measured for all tornadoes in the United States in 2017. I went there to find this, and I couldn't find the damn file. Okay, and Michael Sullivan's a good guy. I actually know him pretty well. And he teaches at Joliet Junior College, so he's a good guy. But it wasn't there where I could find it. And I thought, damn it, I wanted to do this problem because, and I'm telling all the students in the class, I really like problems with data in them because you have to go get data and you have to do things with it, everything else. So I really liked this problem, and I was really almost angry when I couldn't find it. Okay. But I kept the problem, and then I said, well, maybe I can find on the internet somewhere something about probabilities. So Linda's going to go to the very next slide, and this is the slide that I found. Now this is talking about tornadoes. Now it's not exactly what Michael Sullivan had, because he had all the tornadoes in 2017. Actually, I don't know what he had because I couldn't find it, but I found this on the internet, and you see that we have different classifications, and this is called a Fugit. Actually, I don't even know. I'm not sure how I say that. It's the F scale, but F0 is a weak storm, and F5 is the worst storm you've ever seen in your life. And there's all kinds of data here about these tornadoes. So we can do at least some of these problems. And in fact, now, and Linda's going to hate me because I'm making her type this in. And by the way, I'm not going to want you guys to be typing a lot of stuff in. There might be some problems I ask you to type some stuff in, but I'm generally going to try to say, hey, there's a file there, go grab it and do something with it. And that's really what I wanted to do with this, but I couldn't do it. So Linda, let's just do the January through December, those numbers, and forget about what they are, Fs, okay?
So which am I doing?
The first two columns.
Okay.
So Linda's typing in the first two columns, and we'll do some of this problem. Now, and I'll just go back and repeat what it said. It said, find out a probability model for when do tornadoes happen. Okay, well, we have by month here, so that was good. And it said, come up with a probability distribution. That does go into December, Linda, somewhere. Okay, so now she's putting the number that we have of the, oh, actually, yeah, okay. And was there 0 in December?
Yep.
Okay. All right. Now, Linda, scroll over to see if they added those up or not. See, that really is F question mark.
We have totals down here, but not going across.
Okay.
Well, not up and down. Can I make a request for the dice problem? I feel like that one would be really good.
Okay. All right. Now there is the dice problem is there somewhere.
Okay.
That would have been a great problem if the date had been there and if Linda hadn't, you know, not wanted to type those numbers. Okay. Now, and by the way, Linda, I've changed this a little bit. I mean, this is, we are going to do the dice problem here, but, and I don't know what number this is. What number is this? Maybe you don't know.
This is 9.
9. Okay. So here's what we're doing. We're tossing 2 die. They are fair die. And I said, what's the probability of getting between a 7, between a 4 and a 7, inclusive as the sum of the 2 die? Okay. So now, Linda, we're going to do this twice. The first time we're going to do what's called a simulation. And I am going to, and this is the last section in chapter 5 in Sullivan's book. I am going to lecture on this, but I'm talking about it even tonight. So we're going to do a simulation of what happens here. And so Linda, we're going to go to Excel and we're going to do a simulation. So Linda's going to go to simulation. And now, Linda, we are going to do what I had, but call that first one the, oh, I don't know, blue die, or just call it blue, and the other one can be whatever color you want, except blue. Okay, so these are blue and green. Now, what Linda's going to do is she's going to get random numbers for all of these things. And so what she's going to do is she's going to do a random between, and this is going to be 1 and 6. Okay, now, and that time it got 1. But she's going to pull this down. And Linda, let's just do 100 of these. So Linda's pulling it down all the way to 100. And that's going to be 101 because she used the first one for the color. Okay, now everybody can see that that generated things. Kathy has a question. Go ahead, Kathy.
So just to make sure I'm understanding, you put the formula in, but the formula is actually rolling or simulating rolling, picking a number, so it's going to be different every time, correct?
Yes,
Yes.
and and Kathy, it's even worse than that because it's but by the way, you said that really well, so good for you, okay?
Thank you.
But it's even worse than that because this is a volatile formula, and that means every time you touch it, it changes what it is. So you see, when Linda touches one of those things, she's touching something, it will change. But now what we're going to do is we're going to do the next one. We're going to do the same thing with green. And she's going to pull it down. So see, we're doing this experiment 100 times. Now, Kathy, we're about ready to change this so this isn't volatile. But and Linda knows what we're going to do. We're going to copy and paste this. Now, I am telling you that, and one of the reasons I wanted to do this, and I want to hear what Kathy says before you do that, Linda, because I want people to be able to. Linda's doing it anyway. Okay, but I have had students in this very class who didn't know how to do what Linda's going to do in just a minute, and they had real trouble on a test. And of course, I went and I talked to them, but part of me said, well, you're supposed to know how to do this, but here's what you do. But what you want to do is understand this. So now I am calling on Kathy, but Linda's now in just a moment going to deal with changing these things so they're not volatile anymore, so they're just numbers. Kathy, now I want to hear your question.
Would you be able to use that same formula random between if you wanted to do individual numbers, like let's say you wanted to find out the chance of rolling an odd number, would you put 1, 3, 5, or would that not work?
This function here just gives you random between two integers. There's a whole bunch of functions, and in fact, Linda, wanted to do that other thing, but we were going to do even some random real numbers. But no, you wouldn't do that to get odd. You'd say random between to get that. And there's other things that you can do here. But
Okay, thank you.
so that is okay. Now what Linda's going to do is, you see, we don't want those to be volatile, and so she's going to copy those, and she's going to paste. So she's copying them, and then she's going to paste special. And the pasting special, it says paste as numbers. Okay, so now she's done that, I think.
They changed, but it worked.
But now that you see, that doesn't change. Now those are numbers. It worked. Okay. So now what Linda's going to do is she's going to put the sum in column C. So she's going to say, all right, I'm adding them up, sum. And now what we're going to do is we just add those, and she's doing it that way, which is fine. That's how I would do it. And then she's pulling this down. But see, now she's getting numbers. So that's what we get for the sum. Now, Linda said she wanted to look at a probability distribution. So Linda, I'm going to ask you now to, and Linda, let's go over here somewhere and let's write X and P of X. But above this, Linda, like in G, I don't know, G3 or something, right above there, put simulated. Because you see, we simulated this. This is not a theoretical thing. This is a simulation. So, and again, Linda's going to put in the X, you could get 2 up through 12. So that's what you can get for the sum of the two. But now she's going to go over and she's going to sort those things by column C so we can count them.
Oh, that's way too much work. Just use a COUNTIF function. Let's see. That didn't get the whole name. So I'm looking from C2 to C101. And the criteria for this is equals 2.
Now you really want to have it clicking on the 2 so you can pull it down, right?
Yeah. But I think I'm going to have to actually change that a little bit. But I can do them individually. Okay.
And class, just between you and me, we'd be finished with this by now.
What? Not even.
Now, what Linda is eventually doing here, she's counting how many of each thing you got, and then she's dividing it by how many we had, which was 100. And one day she'll divide it by 100.
Eventually.
Yeah, yeah.
Hold on. I promise it really is more work to try to count them.
Now, what she's putting in this PX column is not PX, it's something else, okay? It's just counting how many times it happens, but then she's going to divide this all by 100. Yes, Kathy.
Could you explain what, I don't really understand what Linda is changing or doing in each tab
Well,
as she's going down?
Yeah, and we're going to do this twice. I mean, we'll do what Linda does, and then we'll do it a way that I think some of you might understand maybe better, but we'll see. Okay, so she's just using this fancy Excel function to count how many of each thing you've got.
So the first thing that I have before the comma is the range that it's looking in. So this formula is basically saying to count if it has that value. So it's just counting the number of cells in this range that meet the criteria that I'm specifying. So here then, since I dragged it down and I didn't specify to leave it how it was, so I need to change the range for it. And then I'm changing the criteria for each one so it matches what the X is.
And then she's going to have to divide all these numbers by 100.
Yes. So let's see.
So, excuse me again. So essentially, Linda, you're typing in, like in the last one you just did, you were saying between cells C2 and C whatever, how many times did you find 12? And then it's showing
exactly.
You, okay.
So then, since I have all those numbers now, then I can just divide that, and I'll change these. So this is count, and this will be my probability.
Now that had better add up to 1, okay, and I think it will. So Linda will add that up to, just add that up. That's just a little bit of a check. Okay, now that's what you would have done if we had been able to do the problem dealing with the tornadoes and things like that. So we made a simulation to figure out what happens here. And if you look at this, what you see is that you have different things that happen. The most frequently occurring event in our simulation was 5, and the second most was 7. But it turns out that just happened in the simulation, but this gives you an idea of what you what might be happening here. So anyway, that's what we have for our simulation. But now, Linda, and on the same page, and I know, Linda, you and I have done this before, so we're going to make a little grid, and we're going to figure out theoretically what it is. So this is going to be theory instead of that. So you see, she's saying, well, that's going to be, I don't know what color that is. She'll make a color for that. Is that the blue?
It'll be something.
Okay. And then she'll do the other one. So one will be the rows and one will be the columns. Now, I got to tell you guys, I have asked questions like this on exams before, and students make little pictures like this to count. So that's the green, and the other one's going to be the blue, I guess. Okay, so that's the blue, and she's going to put all the numbers in there that are the sums.
Ah,
Now, one thing that you can observe then is, first of all, there's some very nice symmetries that you see. These diagonals have the same numbers in them, and this is the sample space showing you all the possible outcomes that you can get. And this is a theoretical model, so we're going to actually come up with the theory. What should this supposed to be? And the law of large numbers said if we did this simulation more than 100 times, if we did it a gazillion times, by the way, a gazillion is not a real number. What we can do is we can go through and we can figure out probabilities, how many things we've got. Now, so Linda's doing the theoretical probability here. So this is P of X. So this is what it will eventually be. Okay, so she's going to count how many things you get, and she's dividing everything by 36 because there are 36 different outcomes.
that should be 1.
And where she's getting the numbers is, she's really just counting those diagonals. Oh, this is me. Okay, so this diagonal here, so that's how she gets things. And you notice she had a formatting hiccup here that she'll have to go fix in a bit. Yes, Kathy?
I feel like this is a silly question, but why did she add up in the table at the top? Why did she add up the top and the 2 columns, or the column and the rows?
Oh, because that's how this game is played. If you're playing Monopoly and you take a pair of dice and you throw it and you get a 3 and a 5, you move 8 spaces,
Okay,
yes?
okay. Yes, okay.
So this is like a Monopoly game, kind of.
I thought it was a chance of rolling a 1 and a 1 or a 1 and a 2. Okay, sorry about that.
You see, the chance of getting a 3, there's 2 ways you can get a 3. You can get a 1 or a 2, or you can get a 2 or a 1, and those are counted separately because one die is blue and the other one is green. Okay, so those are the theoretical things. Those should also add to 1. And so what you can see is, gee, your simulation wasn't exact, but it gave you a pretty good answer. And you can see that theoretically, the thing that happens with a chance of 1 out of 6 is 7. So 7 is the most popular score. Okay. Now, the question, Linda, I think I asked was, what's the probability of getting between a 4 and a, was it 9? I don't remember.
7.
Was it 7? Okay, so you need to add these up. And the reason you add them up is, you see, if you get a 4, you don't get a 5, you don't get a 6, you don't get a 7. You add these up because these are disjoint probabilities. And so the probability is you would add all those numbers up. And Linda's writing, but now she's using formula. She said this is equal to that sum. She would just add those up and she will get that. So that says there's a 50% chance of getting that. Now, I asked you to do it if she went over and checked that on the simulation between a 4 and a 7. And Kathy, I'm not ignoring you. I know I am a little bit, but not for long. So she's going over to the simulation and she's figuring out what happened in the simulation. If you really didn't know what was happening, you see you get that. And that's pretty close. It's not exact, but it's pretty close. Yes, Kathy?
Can you just talk through that, how you wrote out the probability of 4 is, because I would have written a different way. I'm not sure how you knew to put the less than equals in the less than. Just walk me through that one, the last form. Yeah, that. Thank you.
Here's what I
That was just my notation. So since we're doing the probability of 4, well, between 4 and 7 inclusive, then that's why I have the equal signs, just to, so I know that we're including those numbers. And then the less thans just tell me the X is between those.
And that just has to make sense to Linda. If you're doing a problem like this, you type something that makes sense to you,
Okay.
so you know what that number is. Okay, I'm going to ask another question. I'm just going to ask Linda to write it. Oh, Lori has a comment. Yes, Lori.
I just wanted to verify. So all you're doing is, when you're saying that we're trying to find out how often the sum will come up as anywhere between 4 and 7. All you're doing is adding up the probability of all of those, and that's it. The probability of it coming 4, 5, 6, and 7, and that's your answer.
Yes.
That is, but Lori, there was one other thing that was underneath all that. The reason that I can just add them up is they're disjoint events. You see, if you get a 4, you didn't get a 5. And if you get a 5, you didn't get a 6 or 7. So those are disjoint events. That's why you add those. And in the lectures, we find that, if there's intersection, you have to be a little bit careful because you don't want to do double counting. But what you said was fine, and I'm just saying more because I don't know. I think I should.
This type of probability, that's how you do it. Is what you're saying.
Yeah.
Okay.
And by the way, there's other problems that are like this, and maybe we'll get to that. Linda, for some reason, wanted to do this problem, and that's fine. Okay, I want to keep Linda happy because she makes major contributions to this class. Okay. And I also, I think people just should be happy. I hope people can be happy. Okay, so, all right, now Linda, we're gonna invent a new problem on that same one. So stay on that same thing. There's a game called craps, okay? And here is how the game of craps works. You go and they give you the die, and this is your first throw. If you roll a 7 or an 11, you win on your first throw. So Linda's going to type this, and Linda's just a few words. What's the probability of getting a 7 or 11 on one throw? Okay, well, you all know what numbers you're going to add together, yes? 7 or 11. And so Linda's going to look at her probability distribution. And so you're getting a 7 or 11, and she's just showing you in the sample space, but you can just go down to her probability distribution and add these two. So you see you're getting that. And then the other 11, and this is going to be on a diagonal as well. Seven or 11 is equal to. And so you could just look at that and you could say that that is 8 out of 36, or you could go over and add up 7 or 11 numbers over there, and you get the same number, okay? So I just made up another problem, but I think that's a good problem to ask too. Questions on this before we move on? Lori.
So if you changed it to saying, what's the probability of getting 7 or 11 in 6 throws, then how would you change how you did this?
Wow. Okay. Lori, that's something I plan to talk about, but I haven't talked about it yet. And you're saying that and that's a different thing, and that would be an example of a binomial probability, and we will talk about that distribution. We haven't talked about it yet, and so what I'm going to do is I'm going to defer that question just because it would take us on a super tangent. Now, I am going to ask, and Lori, I think you've been, having perfect attendance and stuff like that. So, you remind me, but we will get to that, okay? And in fact, I'm finishing up chapter 5 in the lectures, and I will be going in and talking about the binomial distribution. And I can answer that, but I'd really rather answer that with a tool. But that is a different question. You're exactly right. That's a different question. Okay, so to be continued with that. I mean, I know the answer and Linda knows the answer, but it really would be a disservice to go back and develop all that theory here.
We're still working on the baby steps right now.
Well, but also this stuff, I want to stress this. This isn't trivial, and I'm going to talk to you a little bit about a math history, okay, for a moment. But there was a real smart French guy named Pascal. And there was a gambler who consulted with Pascal, and he said, I have a game of chance I want you to give me some advice on. And Pascal had to think about this for a long time. the question. And in fact, he corresponded with the great French mathematician Fermat over several months. And they basically were inventing probability theory. So even though Linda said that's a baby steps, and I agree, Linda knows a lot more probability than what we're covering here, and we will cover more probability, but this isn't trivial stuff. And Pascal and Fermat, two of the smartest dudes who ever lived, corresponded over months debating this problem, these kind of problems. So it's not trivial stuff. So if you're saying, well, I'm having to think hard about this, stuff like that, that's okay, because it's not trivial things. But we are doing some pretty elementary stuff. Linda, let's try another number now, unless somebody else got a question. Okay. Oh, wait, Kathy, yes.
I was just wondering, can we go over one of the ones that involves the cards? I remember from the video I had a bunch of questions.
Okay, if Linda will go, and now
If that's okay.
But no, I'm fine. I don't. When I say I don't care, I mean, you know, as long as we're learning, that's all good. And that will, now Linda's looking for a card problem. I know I put at least one there. Okay, and there's two of these. I don't know, we might do both. Okay. Actually, Linda, there's even another card problem that talks about, Linda, there's another one that's three of a kind. Let's only do one of these, and then we'll maybe, and so Kathy, this is for you. And Kathy, do you want to do 31 or 33? Or 31 or 32?
I don't
doesn't
mind.
matter.
Doesn't matter. I just get a little confused because they're throwing in another variable of the different what is it, the suits. So I just remember being confused in the video, the pre-videos.
Okay, all right. Well, let's do this. Now, we have to review a little bit, and there are pictures in the video. I showed you a picture of a deck of cards, but what you have is you have ranks of cards. So they go ace, 2, 3, all the way up to 10, and then it is jack, queen, and king. And so there's 13 ranks that you have for the cards. And then you have 4 suits, and the suits are hearts, diamonds, spades, and clubs. Okay, so that's you know, that's what you get. So that's what a deck of cards look like. All right, and a deck of cards, since there's 13 cards of each suit and there are 4 suits, there are 52. 4 times 13 cards. Okay, and it says as shown in figure 7. Well, that was a figure that, you know, I didn't replicate that here. Okay, and Linda's doing fancy stuff there. That's good. Okay, but now let's look at part A. Now, I am going to tell you, Kathy, and everybody else, that since we're talking about the probabilities, the denominator is probably going to be 52. Okay, but part A says, compute the probability of randomly selecting a heart or a club from a deck of cards. Okay, now, the probability, how many hearts are there? There are 13. And how many clubs are there? There are 13. And Lori, I hope you're listening, because if you're a heart, you're not a club, and if you're a club, you're not a heart. So those are disjoint. They don't overlap. And so what you get there is you have 26 divided by 52, and that's going to be 1/2, or 0.5. Okay. Now, the next one says, compute the probability of randomly selecting a heart or a club or a diamond. And Lori, I'm not picking on you, please understand that. But if you're a diamond, you're not a club, and if you're a diamond, you're not a heart. These are disjoint sets. And so there's 39 of these cards divided by 52, and that's going to be 3/4, or 0.75. Okay, so that is B. Okay, and now let's go to C. Now you're getting an ace or a heart. Now, hey, everybody pay attention to this, because this actually brings up something new. And Lori, especially you pay attention to this, because you see this overlaps. Because you see, it says, what's the probability of selecting an ace or a heart? But we have an ace of hearts. So it overlaps. So how many hearts do you have? You have 13. And how many aces do you have? You have 4. But one of those was the ace of hearts, and you can't double count him, so you subtract that off. And so what happens is you will get 13 plus 3 is 16 divided by 52. And I did that in my head, but I probably did that right. So anyway, so that's what we get for that. And Lori, and again, I'm not trying to pick on you. Did you understand the distinction I was making there?
I did.
Okay, and everybody else, yeah, you're saying, oh, he just cares about Lori. That's not true. But Lori asked a question, and I was trying to build on that. We good? Kathy, you good? You started this mess.
I had a question too, just the way we write down, because it's probability, are we always leaving it at, for instance, the probability of a hard rock club, we would leave it at 0.5, we wouldn't ever change it to 50%?
I don't so much care. I would count either one of those, right?
Okay, all right.
Okay, so I mean, don't worry about that. Linda will tell you that I'm anal about some things, but I'm not anal about that. Linda, try to find the problem that is called 3 of a kind. Since Kathy wanted to talk, and I don't know where it is, I'm sorry.
Oh, I had one other question too, and maybe you had already, I had to step away for a moment, maybe you had discussed this earlier, but in the video there was a phrase that you kept mentioning that was confusing. I didn't really understand what it meant when you were saying the probability of E given E minus F, or something with the given E of F. Can you explain what?
I certainly can. But what I'm thinking about is, and I always know what time it is. I know exactly what time it is right now. So we're going to do this this 3 of a kind problem first, Kathy, and then we'll talk about that. And that's called conditional probability. And so we'll talk about that. And I do have problems here about that too. Okay.
Will we be?
But
Oh, excuse me. Will we be continuing probability next week as well?
Yeah.
Okay.
But we're gonna. I mean, we'll just keep. I mean, I don't know. Yeah.
Okay.
The answer is yes. Okay.
Okay. Thank you.
Okay. All right. Now I have to read this to you, and you have to think a little bit about poker here. So this is 3 of a kind, and this is draw poker. And by the way, it used to be that people played draw poker back in the days. Wow, I don't know how I'm getting that feedback, but anyway, back in the day when I played a lot of poker, what happened is people did play 5-card draw, and we played 7-card stud poker. We played a lot of different games. Now nobody plays these games. Everybody plays Texas Hold'em, and it's a way different game. Okay, but here we're talking about 5-card draw poker, and so here we go with this. You are dealt 5 cards from a standard deck, and Linda listed the deck over there, and she even color coded things for you, being red and black suits. Okay, so that is good. Determine the probability of being dealt 3 of a kind, such as 3 aces or 3 kings. It could be 3 jacks and so on and so forth. Now that's actually a pretty good hand, and that often will win, but you want the probability of getting that as your hand. The first thing, though, we're going to do is we're going to talk about the denominator. And think about this, you're being dealt these cards, so it doesn't matter what order you get these. And by the way, in the videos that Kathy was talking about, I go over and over again, it's important to realize if order matters or order doesn't matter. And here, order doesn't matter. So that means it's combinations. So the denominator is going to be 52 choose 5. So Linda's going to write something that's 52 choose 5, and then she's going to use that formula to calculate that. And this is going to be a big ass number. It's going to be around 3 million if I did that in my head correctly. Actually, it's less than 3 million. It's 2 million and some. But you see, there are over 2 million different hands that you can get in poker. And that's going to be your denominator. Okay? But now, so that's part A. It says, how many different ways can you get 5 cards? Well, that's 52, choose 5. And again, the order didn't matter. Okay? Now, I think we know this from what Linda said. I'm just reading problem B. It says each deck contains 4 2s, 4 3s, and so on. How many ways can 3 of the same card be selected from the deck? Now, we're going to do this in 2 steps. And again, if you watched the video, I talked about this being the general principle is if you're doing task 1 and task 2, task 1 can be done M ways, and task 2 can be done N ways. Then the number of ways that task 1 followed by task 2 can be done is M times N. So I'm going to be multiplying probabilities, okay? So it says, how many different ways can 3 of the same card be selected from the deck, okay? Now, and by the way, I'm not sure if I'm answering B or C, but we're gonna talk about this, okay? And I almost don't like the way this problem's written. We're just gonna write the answer. What's the probability of getting 3 of a kind? So first thing is, what we're going to say is, pick a suit. And how many suits are there? There are 4. And so picking a suit is going to be 4 choose 3. You see, you want to get 3 of a kind. So first we're picking a suit. It is 4 choose 3. And Linda's going to calculate 4 choose 3 there for us. And we're going to know what that is. And 4 choose 3 is going to, of course, be 4. Okay. Now, so that's what we get. But you see, this is taking into account the fact that we could go hearts, spades, clubs, or we could do, you know, we're picking 3 of those. So first we pick the suits that we have in our hand, and Kathy, I'll be with you in just a second, but then we pick the rank, and the rank is going to be 13 choose 1, because there are 13 ranks, and you're choosing one of them to have the 3 of a kind. Now we're not finished yet, but this is how we're choosing the 3 of a kind part of this. Now we're not finished with our hand yet because we only have 3 cards. Yes, Kathy.
I don't understand why you would do 4 choose 3. If there are 4 suits, aren't you only choosing one of the suits?
No, I'm choosing, let's talk about having a 4 in the hand, okay? If you have a 4, if you have 3 4s, you're picking 3 of the 4 suits, aren't you?
I don't understand what you're saying. You're picking there are 4 suits.
Linda, all right. There are 4. Linda, we're going to do 3 4s, okay? And pause right there, Linda. Now we're doing 3 4s. So 3 4s means that in her case, we did hearts and diamonds, and then we did clubs, okay? That's one way we could have 3 4s. Another way we could have 3 4s is doing clubs, spades, and diamonds. So you see, we have to pick, we're dealing with the card that is the triple, and so there are 3 of them. So we're saying you got 4 suits, and we have to be counting how many different ways can we get 3 4s. And there are 4 ways that we can get 3 4s. So that's why it's 4 suits, choose 3. Okay.
So it may be easier to think of if you list them out. So you could have a heart. So I'll just call that H, a diamond, and a spade. You could have, let's see, my next one was a diamond, a spade, and a club. You could have a heart, a spade, and a club. Or you could have a heart, a diamond, and a club.
And Kathy, to answer the question that you asked before in the class, you said, how do you know if you're done? Well, I know Linda is done because I did a calculation down here, and this thing down here is 4, choose 3. So there's 4, and she came up with 4, so she has them all.
And Linda, you wrote 4C3, but in the Excel you put 4 parentheses choose parentheses 3. Can you remind me what you wrote to get that?
So what I wrote here is how you'll often see it written on a piece of paper.
Mm-hmm.
So this is just the 4, choose 3 that Bradley keeps saying.
Mm-hmm.
What I did in this column is I actually did the Excel computation. So I used the Excel formula for combinations, the equals combin, and then the way that they have you do it is the first number is the total number of things that you're choosing from, and then the second number is the number of things that you're actually choosing. So because we're picking 3 cards, then that's why I'm choosing 3.
And how did they know from that formula that they were choosing 3 of the same?
Because they want us to find the probability of having 3 of a kind.
And
First you're choosing the suit, then you're choosing the rank.
okay.
And we can keep talking about this at GSG.
Yeah, for sure.
Okay, all right. So that's what we've got. Now we're not finished yet. And Linda, can you go back to the statement of the problem, because I want to write something down.
Right here.
Okay, can you go back to the PowerPoint where that is, because I want to write something. And again, I'm not trying to be rude with that. I'm just saying, yeah, okay. Now here's
you
where,
meant the.
yes.
I gotcha.
Yeah, she and I was not being clear, I think. That happens a lot, doesn't it?
What
okay.
slide is that? 27.
And I want you to think back to that defective sampling problem as I'm talking here, because I'm trying to make this. You see, here's what is happening. First, we pick the card that we're getting, the 3 of a kind. But then there's 2 other cards that you have to have. And those 2 other cards can't be another 4. Because if it was another 4, you would have a 4 of a kind. Okay, so we want to have only 3 of a kind. So what we're going to have then is, and I'm going to use that shorthand that Linda was talking about here, but we have 4, choose 3. Damn, that's like this erases the whole thing, Linda?
Yeah.
Okay, that's what I want to do. Okay, I'm going to try that again. Okay. Okay, so I'm going to say that this is 4, choose 3. That gives me the suits. And then I have 13, choose 1. And this is a multiply that's right there. Now that gives me the 3 of a kind. But then I have to pick cards, and I can't pick a 4, because if I picked another 4, I would have 4 4s. And I said I only wanted to have 3 4s. So if I picked 3 4s, there were 52 cards to start with, and I've already spent 3 of them, so I have 49 cards left. So this is going to be 49 choose. And now you see I'm picking a card, but I can't pick a 4 from there. I'm really trying to think, okay, so that's going to be 49, choose. And I'm going to be choosing 1 card from there. Okay. Now, and that's another multiply. And now I'm going to do another one. And you have to know a little bit about poker to do this, because there's a poker hand that's called a full house. So you see, I can't match this 4, but I also can't match this, whatever card this was, either. And so the next one is going to be 40. Let's see. So I've got 4 cards that are done. So this is going to be 48, choose 1. Now that is my numerator. I have to multiply all those things together. But notice that I do have 5 cards now, because here are 3. Here's 1. That's 4, and there's the 5th card. This all together was how I got my 3 cards. Okay. So you see that added up. So I have to multiply all those things together, and then I'm going to be dividing that by 52. Choose 5. Which is that 2 million number. Now, Linda, I just wanted to be able to write that here in this way. I'm going to turn that back over to you with the Excel, and I'm not trying to make you talk a whole lot, but let's just go there, because we have to multiply all these numbers across the top and then divide by that, and that will tell us the probability of getting 3 of a kind. So Linda's going to go back to Excel then and actually do these calculations that we had there. And she's done a bunch of them already, I think. And she's going to multiply. Yeah, there is. Kathy, go ahead.
I'm just wondering, will you be asking a question similar to this on the midterm?
Linda will tell you I really am not thinking much about the midterm. I could.
Mm-hmm.
Now this is not an easy problem, but I think you're understanding it, and so I mean that's good. Okay, so it's that number divided by that other number. Okay, now look at this. So you see the chance of getting 3 of a kind is between 4 and 5 times out of 100. That means that's a pretty good hand, okay, that you have. And by the way, we didn't necessarily do the A's, B's, and C's over here, but we actually talked about all of this problem. Okay. Now, Linda, let's go to, and I'm trying to respond to Kathy's question. There's a problem that deals with conditional probabilities, and it's the one where we're just doing the calculations with it. I think that's the one we want to do. I think you'll recognize it. Yeah, that one. Yes. Okay. So whatever that one is, let's go to that one.
Okay.
All right. And Linda's doing good things here, but I'm going to go back to that slide, and I'm going to write on that slide in just a minute, because I want you to know the formula that Linda's using.
All right. Let me get back there.
Okay, good. Thank you. Okay. All right. So now I'm going to remind you of the formula. Okay. And someday there it is. Okay. Now this is the formula, and this is in your grace notes, so you don't have to memorize it, but you have to know what it says. And so here is the formula, and I'm trying to think the best way for me to do this. This is probably the best way. Okay. So this is the probability of A given B. Now I lectured on this in the videos, and this says that's the way you read this. This is the probability of A given B. So you see what we're assuming is that B has happened, and so what's the probability of getting A given that B has happened? and this is equal to, this is the formula. You take that this is the probability of A and B. This is the word and B divided by the probability of B. And this is called conditional probability. And I spent the better part of a lecture, of a video lecture, talking about this, but we're going to do it. Now, number one is not an interesting problem at all. It says, this means the probability of event F given event E. That's just the way you read that. But now Linda's going to go back to Excel and we're going to work those. But this is the formula that you all want to be thinking about when Linda's working some of these problems. So Linda, go ahead back and we'll do some things. And don't worry, folks, I know what time it is. Okay, go ahead, Linda. You can go back now and Linda, just pick one to do. In fact, Linda, how about, wow, let's do number 2.
Okay, so they're saying the probability of E is 0.6 and the probability of E given F is 0.34. So they're asking if E and F are independent. So
now
if
I'm going to pause and say that we're going to do this in 2 steps. So Linda's going to use the formula to figure out what is the probability of E and F. And we know from the lectures that I gave that the probability events E and F are independent if the probability of E and F is equal to the probability of E times the probability of F. So Linda's going to use the formula that I wrote to figure out what is the probability of E and F.
Okay, so I'm multiplying the probability of F given E by the probability of E, which I don't think they gave me that. Bradley, I'm going to let you take this one. Because I feel like that should be the other way.
It should be, but we actually can, I think we can figure it out from that. I'm very conscious we have, tell you what, let's circle that and I will talk about that next time. That'll be a leftover. Okay, let's do number 3, Linda.
Okay. So we have E and F, so we're basically just plugging these in. So this exact formula up here is what we're doing. So let's see. I have E and F is 0.6, so I'm doing 0.6 divided by the probability of E is going to be 0.8, so 0.75.
Now, and actually, Kathy, and I know what time it is, and I want to hear what you have to say. But Linda, we're going to do this right now. We're going to go back to this and do it right now. Now, I'm using something that I did talk about in the video. And again, if you haven't watched the video, you know, you haven't seen this yet. But here's what I said in the video. If E and F are independent, if E and Linda, maybe you'll type this somewhere. If E and F are independent, the probability of E given F equals the probability of E. You see, if E and F are independent, F has nothing to do with E. So the probability of E given F is just the probability of E. But the probability of E was 0.6. What's the probability of E given F? 0.34. They would have to be equal if they were independent. Therefore, they're not independent. Now, Kathy has a question, and I do want to hear her question. So, and I am watching the time for you guys. I always know what time it is. Go ahead, Kathy.
No, I actually don't remember my question. I'm very confused. So I'll talk to you in the GSG or office hours. I'm not following when I guess I don't understand. I also don't understand. This is another question. What is the difference if you could explain it when they're saying the probability of E and F, how is that different than saying what is the probability of F given E? If again, in probability of F given E, they're both happening.
Okay, I'm going to give you an example, okay, of things that are independent and things that are dependent. And I'm going back because you see, to understand the conditional probabilities, you have to have a firm grasp of this other thing first. And in the last 3 minutes, I think I can try to do that. Okay, so here is the deal. Linda and I interact quite a bit on Tuesday, but there are other days when we don't interact at all. Okay. But I will tell you something that is a dependent event. If I don't have a good breakfast, I'm probably not going to have a good day, because breakfast for me is the most important meal of the day. So good breakfast, then probably good day. Those things, so that is dependent. But if Jim has a good breakfast or not has, unless it's a Tuesday when Linda and I are working closely together, whether I have a good breakfast or not has nothing to do with if she has a good day. So this has to do with independent and dependent events. And before you can understand these conditional probabilities, you want to have a good understanding of that. So I think that's where we're going to go. Now, we are moving along, and these are kind of my closing remarks tonight. This isn't easy stuff, and we're going fast because I'm supposed to teach you a lot of stuff. But I'm also going to tell you that you guys are okay. I've flown this plane many times. I've flown it through COVID skies many times, and Linda's been my my cabin mate on these things. And Linda, people end up okay, don't they?
Yes, they do.
Okay, because Linda and I know how to fly this thing, and so we'll get you there. Now, is it going to be easy? No, the subject's not easy as well. And gee, this would be so much better if we were in a classroom, because Linda and I would just say, hey, use your workstations, and we'll walk around over your shoulders and look at what you're doing and things like that. We can't do that here. And that's the reason I say keep your seatbelts buckled and your tray table stowed, but have faith in Linda and have faith in me, and we will land safely together. Okay, so that's my thing. It's not going to be easy, and are you going to have to work? You bet. I expect you're going to have to work and things like that, but we will get there. Okay, and so you know that. And I guess I keep talking and want the clock to change to 4-0, but it's just not happening. So maybe I was talking too fast. So anyway, we're finished for the night. I do have office hours in, I don't know, 20 minutes or something like that. And Linda's going to turn the recording off too, and she'll probably end up posting this sometime.